Okay, thank you. So I'm Rudolf, and I'll be presenting the paper Security Risk Optimization for Multi-Cloud Applications that I made in collaboration with professors Domagoj, Jakobović, Dejan, Škvorc, Stjepan, Groš from the University of Zagreb, Faculty of Electrical Engineering and Computing. In the past decade, maybe decade and a half, cloud platform became very popular due to its scalability and pay-as-you-go model. But the main issue that companies usually have when they're moving their services to cloud is trusting their cloud service provider, or CSP for short. How can a company be sure that the cloud isn't looking at their data? Client-side encryption helps in this regard, but it also prevents the data from being used by the applications running in the cloud. So this sort of defeats the purpose of using the cloud in the first place. And this is where the multi-cloud comes in. It turns out we can use multiple cloud providers simultaneously to mitigate reliance on a single cloud provider. In other words, we can reduce the security risk by optimizing data distribution among available cloud providers. So we just have to be clever about which data goes where. In order to optimize the risk, we need a model. In our model, we assume that the application and the database are both distributed. So the database is split into database fragments. Each of those fragments can be stored on any of the available cloud providers. And each of those fragments carry information. So it needs to be considered a resource that needs to be protected. Application is split into components. I'm sorry, I can hear somebody speak. So the application is split into components, C1, C2, and C0 in this example. And each of those components can also be deployed to any of the available clouds. And each of those components can also access any data fragment and send and receive data from other components. Results exchanged between components are also considered a resource that needs to be protected in the risk estimation, because they also carry information. So they also need to be in the risk assessment model. Previous work on the use of multi-cloud to increase data security only used database fragmentation. So they didn't consider application fragmentation to increase the application security. In our model, we use security constraints to specify sensitive data relations. So they are a way of saying, I do not want these resources to be available on the same cloud. So in this example, we have a vertical fragmentation where person name and surname is split from the payout amount. And then these fragments are deployed to different clouds. So in the event of data leak on one of the clouds, the attacker cannot link a person to a payout amount. Formally, a constraint is a set of resources, and this constraint is satisfied if and only if intersection of sets of clouds where each resource in the constraint is available is an empty set. Determining where each resource is available is done like so. So this is a set of clouds where resource row I is available. So for fragments, fragment is available on the cloud that hosts a fragment itself and all the components that access this fragment. So in this example, fragment F1 is available on clouds that host the fragment and components C1 and C0. And for other resource, this is result exchange between components. Result exchange between components is available on the clouds that host destination components, so C2 in this example, and the source component C1. Using this model, we can define two risk metrics. First one penalizes violated security constraint, and the second one is responsible for pushing more important resources to more trusted clouds. Therefore, we assume that each cloud, each available cloud has trust estimate, where higher value means that the cloud is more trustworthy. So first metric is calculated. So violating a constraint KL produces a risk that is calculated by dividing the penalty for breaking a constraint with the trust estimate of the cloud where the constraint is violated. So if multiple clouds violate the constraint, we simply use the lowest trust estimate of the bunch. Second metric, resource, so security of an individual resource is calculated by simply dividing the value of the resource with the trust estimate of the cloud for every cloud where the resource is available. Our solution is represented as a mapping of fragments and components to the cloud providers. So here is an example of a solution where all the components are mapped to sigma 2 and fragments are split between sigma 0 and sigma 1. Our crossover operator simply iterates through all fragments and components and then simply picks a cloud from one of the parents uniformly. So this is where the crossover is visualized. For example, F1 here was picked from parent B since it is assigned to sigma 2 in parent B. Mutation operator, we use two of them. One that completely randomizes the solution and the other one that picks a random fragment or a component and assigns it to a random cloud. For optimization, we use NFGA3 because of its multi-objective nature to avoid assigning importance to those risk metrics before the optimization that we defined earlier. Because those risk metrics have very different scales. Our test application consisted of 10 data fragments and 10 application components. We assumed that 7 cloud providers was available, whereas sigma 6 was most trusted. So this setup yields 7 to the power of 20 possible solutions. And we defined 10 security constraints and set the penalty for breaking each constraint to 100, so it was the same for all constraints. And after 100 iterations with the population side of 500 solutions, we got something like this. So it's a nice Pareto front where we can explain, I don't know, solution A and solution B are the most notable ones. Solution A has a low single resource risk, but it has the highest constraint risk because it violates 3 security constraints on the clouds, sigma 4, sigma 5, and sigma 6. Compared to all other solutions in the image, this is the worst constraint risk. On the other hand, solution B breaks only 2 constraints, and both of those are violated on the cloud sigma 6, so on the most trusted cloud. But the solution B pays for this by placing more significant amount of resources on less trusted clouds, so the single resource risk is quite high here. Compared to the baseline, we simply used our random search. We never could achieve anything close to this, so single resource risk could never go below 2,500 or so. And to conclude, we proposed a security risk assessment model for assessing the risk of multi-cloud database and application. And using the model, we performed multi-objective optimization that provides the user with the Pareto set of optimal deployment strategies. Further work is focused on dealing with these assumptions. So how to make flexible databases and applications to be more easily deployable anywhere we want. So the optimization is more free to do anything. And how to define security constraints, and this is more this is very taxing on the user since there are a lot of resources in the application. So this is it, and thank you for your attention.